Hello there, my name is Charles Sulasfani Msipa. Welcome to another presentation on complex functions. In this case, we're going to look at computation of residues, but the exercise we're going to look at now, we're going to also briefly look at zeros of rational functions combined with the computation of residues. Now, let's say we're given an exercise which reads as follows. Given f of z equal to z cubed minus z over z minus 2 squared multiplied by z squared plus 4. Now, this says requires us to determine the zeros and poles of f of z, and in the second part to determine the residues at each pole on the complex plane. Now, as solution, starting with the first part, where we need to compute to find zeros and poles. Starting with zeros, remember z0 equals to a is a zero of a function if the value of the function at a is equals to 0. Now, for a rational function like this one, we should recall that any fraction whose numerator, let's say 0 over d, where d is not equal to 0, it's always equal to 0. Otherwise, I'm saying that whenever we have got a numerator equal to 0, then the whole rational expression must be equal to 0. So because of that, to determine zeros of a rational function like this, we simply need to grab the numerator, in this case, which is z cubed minus z, and set up an equation. In this case, we will treat as z cubed minus z equals to 0. Then solving this equation will then determine the zeros of the function. In this case here, you can see that this equation is equals to z bracket z squared minus 1 factorizing, and this tells us that this is also equals to z bracket z plus 1 z minus 1. Maybe notice that this is a difference of 2 squares, and then this equals to 0. Now, solving this equation, we can clearly see that these solutions are z equal to 0 or z minus 1 equals to 0 or z equals to 1 is 0. So in this case, this function has got 3 zeros, which are 0, minus 1, and 1. So the zeros are determined there. Maybe let's say denote them here as zeros of f of z, giving them as a set. We'll have here zeros of f of z equals to 0, minus 1, and 1. So that's the complete set of the zeros of f of z. Now, this is part A of 1. Part B of 1 will then determine the poles. Now, the poles are precisely what are zeros of the denominator. Now, it's to determine the poles given a function f of z equal to a numerator, expression of z, over a denominator expression of z. To get the poles, we need to set up an equation which says dz denominator equals to 0. Then solving this equation we're going to get our poles. In this case, here we've got z minus 2 squared multiplied by z squared plus 4. Now writing z minus 2 squared multiplied by z squared plus 4 equals to 0. This equation, solving this equation, will, like we've said before, will give us these poles of the expression. In this case, we can see that here this factor is repeated, which means that we're going to have a double pole, and that here we can factorize as a z plus 2i multiplied by z plus 2i multiplied by z minus 2 all squared equals to 0. So in this case, this would mean that z minus 2 squared equals to 0, or z minus 2i equals to 0, or z plus 2i equals to 0, which in this case therefore gives us that z equals to 2 twice. It's important to state that this is a double pole. By saying twice here, we're stating that this is what dealing here with a double pole. And then next, z equals to 2i, which is a simple pole because this factor occurs there once, or z equals to minus 2i. So here we've got a complete set of poles of f of z. Now we can proceed to determine the residues at these given poles. Then this is what we can do. We're given the function f of z equals to z cubed minus z all over z minus 2 all squared multiplied by z minus 2i z plus 2i. Notice that here we're taking the function already with the denominator factorized. Now, remember, now we need to compute the residues. So, identifying our poles, we have here z equals to 2, which is double pole, z equals to 2i, simple pole, and z equals to minus 2i. Maybe starting simple, let's start with calculating the poles at the residues at simple poles. And let's start with the residue of f of z for z0 equals to 2i. We recall that this is calculated using the formula which says limit as z is approaching 2I of z minus 2I multiplied by f of z. We recall that if we multiply this expression by this 2I, we'll have this kind of factor in the numerator. In this case, we'll have that factor with this one simplifying to 1, and we're left with z cubed minus z over z minus 2 squared multiplied by z plus 2I of, in this case, we're going to calculate the limit of z is going to 2I, limit of z cubed minus z over z minus 2 all squared multiplied by z plus 2I. This is after carrying out this multiplication. And then we observe that this is 2I, and this expression is defined 2I. So we can complete the limit by simply substituting 2I in the expression and simplifying, in which case which will be equals to 2I cubed minus 2I over 2I minus 2 all squared multiplied by 2I plus 2I. Simplifying this, here we get 8 minus 8I minus 8I minus 2I over 4I multiplied by 2, let's say minus 2 plus 2I all squared. So all what we're left with here is simplifying this by removing brackets here and simplifying the numerator, where the numerator gives us minus 10I all over 4I. And remove the brackets here, having a plus b squared situation. We're going to have here now simplifying this expression. We've got minus 10I over 4I in brackets, expanding this bracket using the general form of a plus b squared. We have here minus 2 squared plus 2 multiplied by minus 2 by 2I plus 2I squared. In this case, I squared is minus 1. And so we get here minus 4, which takes us to, we can already simplify here I and I we see that simplifies to 1, and then we've got minus 5 over 2, simplifying 10 and 4, and in brackets we've got 4 minus 8i minus 4, and then minus 4 and 4 simplified to 0, and then multiplied by 2, and notice that we've got minus sign in the numerator and denominator. We've got this as 5 over 16i. This we can simplify if we want to migrate this to the form a plus ib, which is the rectangular form of a complex number. We can then multiply 5 over 16i by 1, and 1 which is written in terms of I over I, which will give us minus 5i over 16. That minus sign originates from the denominator here, but from I squared, it's just from this side, which is in this case we've got 0 minus 5 over 16i, which is our residue in a rectangular form. This is just revising some of the things we have done with complex numbers. Sometimes it's more convenient to leave the number in this form rather than to leave a complex number with an I in the denominator. Now proceeding to the next pole. In this case it would be to consider z equals to minus 2i. For z equals to minus 2i, we write the residue of f of z for z0 equals to minus 2i. A simple pole, in this case, right this way. This would be the limit as z is going to approaching minus 2i of z minus 2i, which will be z plus 2i multiplied by f of z. I hope that you notice that essentially this is repeating what we've done in the previous example. In this case, I'll leave this one here and label it here again. Do it yourself, DIY. Please proceed here and make sure that you practice doing exactly what you did previously, and that way create your own experience. I think now it is advisable to proceed to computing the residue at a repeated pole, which in this case is 2. Now computing residue at a double pole, which is z equals to 2. This is for function which is f of z equals to z cubed minus z over z minus 2 squared bracket z squared plus 4. Now I can write it this way because I no longer need those poles minus 2 and minus 2i and plus 2i. So now the computation, we know that is done this way by this following formula set residue of f of z at z0 equals to 2 for the order m equals to 2. So now here 2 stands for the order and the 2 here is the pole. We can abbreviate this by simply writing residue of f of z at z0 equals to 2 and then 2. According to the notation we've agreed on, this here will represent the multiplicity of the pole, and always how many times the pole is repeated. And for this case, we know that this is equals to the limit as z is approaching 2 of the first derivative of z minus 2 all squared multiplied by f of z. Like I reminded you before, you see that now here we need to differentiate, and these functions are rational functions, so which means we need to revise our techniques of differentiation, especially of rational expressions. So now after multiplying f of z, which is this f of z by this vector, we'll see that we're going to have this vector in the numerator and denominator, therefore simplifying to 1. Then we'll have this limit being limit as z, sorry, going approaching 2 of the first derivative of z cubed minus z all over z squared plus 4. Please make sure that you understand how we end up with this expression. Then continuing, now what we need to do before we can calculate the limit, we need to differentiate this expression, and we note that it's a quotient, so we're going to use quotient rule. So we write here limit as z is approaching 2 of the derivative. In this case, we write the derivative of this expression being quotient rule. We do applying quotient rules. We say z squared plus 4 squared, that is in denominator. Numerator will differentiate the numerator, we get 3 z squared minus 1 brackets z squared plus 4 minus z cubed minus z multiplied by z 2z, with in this case the derivative of the denominator. Now, as you can see that this expression is defined at z equals to 2, we then need to carefully substitute here and simplify. And where our limits going to be 3 multiplied by 2 squared minus 1 brackets 2 squared plus 4 minus in brackets 2 cubed minus 2 multiplied by 2 multiplied by 2 all over 2 squared plus 4 all squared. Simplifying here, you can see that this is 4 times 3 minus 1, which will give us 11, multiplied by 4 plus 4, which is 8, minus 8 minus 2, 8 minus 2, which is 6, times 4 all over 8 squared. So we have 88 minus 24 all over 64. Please check my calculations. The numerical errors must be able to detect that. Then this will be 64 over 64, which is equals to 1, which means that our residue at repeated pole z equals to 2. If all the calculations are correct, it must be equals to 1. Now at this point, this is an example of a multiple pole, in this case a double pole. I hope you notice how we calculated that. This formula, please always read it from the innermost part here, which is here, where you multiply f of z to that, followed by differentiation, then lastly you compute the limit, which you have just done here. Now this reminds us of our whole discussion on how to calculate residues, starting with the simple poles up to poles of order m. Now, summarizing that kind of discussion we had before, we've got the following summary. Now, calculating residues, simple, double, and triple poles. We notice that we have this formula for simple poles, whereby we write residue of f of z, semicolon z equals 2z0, meaning when we write this way, we've got a simple pole, and then we compute the, as we've seen, the residue in the following manner. Now, if it's a double pole, this is what we've just done. We need to multiply f of z by z minus z0 squared, and then differentiate and follow that by calculating the limit to compute our residues. And then for a pole of order 3, the formula, as we discussed it, we arrived at this form that it is 1 over 2 factorial multiplied by the limit, which in this case we differentiate twice, which is 1 less than the order of the pole. After differentiating, computing the limit, and multiplying by 1 over 2 factorial, we get our residue. Now, in the general case of pole of order m, above m of greater than 3, we can put that in this general form as follows. Now let's write residue of f of z at z equals to z0, and the m here stands for the order. What we do exactly what we've done with our pole of order 3, whereby we multiply f of z by z minus z0 to the power m. After simplifying this multiplication, we follow by differentiating to computing derivative of order m minus 1, otherwise derivative of order 1 less than the order of the pole. Then after calculating the limit of the such expression, we then multiply by 1 over 1 m minus 1 factorial, which again here is the factorial of m, or a number 1 less than the order of the pole. It's very important to look at this formula carefully and be able to apply in each case depending on the value of m. Apply it carefully to compute the residues. Otherwise, having looked at the previous examples and this summary of this formula, I would like to say thank you for listening and good luck with your practice.